Hey guys, back in the lab today. I just wanted to show you a little demonstration that I said I was going to show you in weeks before when we were talking about Newton's third law. I guess that was sometime last week that I never got a chance to because I wasn't at school because it was election day, so I figured I'd show this now. Now, this setup that we're using here are these nice tracks and carts that we finally got for this course a few years ago after I basically spent the majority of my adult life at that point begging for some decent equipment, and then we finally got it. And here we have these carts, and attached to these carts we have these force sensors. And so what I'm going to do is I'm going to take these objects and I'm going to hit them into each other, and we're going to be able to see, how the forces exerted on them compare. So I just want to show you this part here first. In the program, which we have loaded on all the computers in the lab, you can see that there are a few options here. And so the first thing you definitely want to do is you want to zero both of the sensors out. And so by zeroing them out, because they definitely have no force exerted on them right now because they're not touching, you're basically just ensuring that they're taking proper measurements. Also, what we want to do is we want to reverse one of them. And we want to reverse one of them because that way, when we collect the data, one of them on the graph will show as positive and the other one will show as negative. And so we'll be able to really get a good sense of exactly what's happening to these forces here. And so I just want to show you this. Now notice it's only going to collect for 5 seconds. And I can actually change that here, notice. And so I'm going to let it to connect for 10, I'm going to let it collect for 10 seconds, just so it gives me enough time. And I'm going to hit collect here. And notice I'm going to push this one on the green cart, and then on the graph it shows that as being the blue line, and on the gray cart that's going to be the one that's showing you that sort of yellowy gold line there. So first I'm going to take these masses off of this cart just so we can do the first one for equal masses. And now we want to be sure that we do this part first, because we really want to make sure that these things totally line up. Because if they don't line up perfectly, then we have a little bit of an issue, because then you're going to have components of forces that are being measured by the force sensor and not the actual force exerted on the thing, and that's going to be a little bit of a problem. And so we really want to make sure these things totally line up before we do the experiment, so we have nice contact between the two. Now, as it turns out, these carts are basically of equal mass, and so we're kind of just going to let it rip here and see what happens. And so I'm going to hit collect, and I guess first, to start us off, I'm going to have the green cart move, and I'm going to have it hit the gray cart while it's at rest. So I'm going to hit collect on here. Now I knocked this off the thing, so this is hard to do by yourself. That's something good to learn. It did measure some force there. So I got these things lined up. Okay, now we're ready. All right, so I'm going to hit collect. All right, so I'm going to hit collect, and I'm just going to have the green cart go into the gray cart. Okay, so the green cart smashed into the gray cart. And notice they actually rebounded again. And look at that. Clearly you can see here the force being measured by both of these sensors is just about the same. Notice the blue line is showing 2.52 newtons and the red line is showing negative 2.55 newtons. Now, of course, because that last digit is estimated and there is a little bit of uncertainty in these measurements, at least at 2 significant figures, that's about dead on. Notice during the rebound too, during the rebound as well, we had 2.16 being measured by the one sensor. You can't really see that behind that time measurement. I can't get that out of there though. And then the other sensor measured 2.09 negative. So those are pretty good, in pretty good agreement. Now I'm going to do this again, except I'm going to take both of these carts and I'm going to smash them into each other while they're both moving. And so the camera's going to get a little wonky for a second because I only have 2 hands. But I'm going to let both of these go. And then we'll see. So I'm hitting collect. They're both in motion. They both hit. And what do you know? The forces exerted on these objects are equal and opposite. It's not perfect, but it's pretty close. Now notice those ones were a little more off than the others, and if you look here now, that's because they kind of came out of alignment. And so we got some of this component issue that I was talking about before. So if we line this thing up perfectly, then we'll see it'll get closer and closer. And so the main point that they're always trying to make here when you're doing this is that it doesn't matter how heavy the objects are, it doesn't matter how fast the objects are going, nothing matters. They always exert equal and opposite forces, at least here with an experimental uncertainty. So now I'm going to have this one heavy, and I'm going to have this one light, and so this one doesn't end up flying off the track. I'm actually going to leave the green one back here, and I'm going to have this gray one slide into it. So I'm going to hit collect here, and they hit, and look at that. The forces are equal and opposite. And even, and this I'm going to try to do here very quickly, even if one of these objects or both of the objects are accelerating, then we still get the same result. And so what I'm going to do here is I'm going to take this little bracket off of the end of this ramp. And so essentially, I just said ramp, but I was going to say, take the bracket off of the track and essentially make a little ramp here. And so notice now that side has no bracket, whereas this side does. And I'm going to take these two boxes and I'm going to put them underneath the other side to just really make that end a little bit higher. So now we'll have a real ramp going here. Now this is going to be a little tough to negotiate. You'll have to bear with me as I get it set up. But I'm going to have the heavier one go up the ramp because I want to sort of use its inertia as a friend so that it doesn't end up going wild on me. And then I'm going to take the gray one and I'm going to have it go downhill, and we'll see what happens. And so notice here, this is going to be too hard for me to show until the very beginning, but it's collecting. And even when they're accelerating down the ramp, we see here that they did hit a bunch of times, 2 times, but notice every time they hit, the forces exerted on them are equal and opposite. And that's Newton's third law. No matter what, the forces are equal and opposite. And for the last thing for today, and I just want to move these off of the track because now it's a little rampy. I'm going to take the 1/4 sensor off of the cart, and I'm really just going to kind of push it into the other one with a varying force so that you're not going to see spikes here, but you're going to see forces that really are exerted over longer periods of time. And so I'm going to hit collect. Okay. And notice, it doesn't matter. The forces are always equal and opposite. And frankly, if you don't think that's cool, I kind of feel sorry for you. Look at the symmetry in that graph. That's pretty sweet. Now, notice what I'm gonna have a little bit of a problem here, which I can tell already, because really what you wanna do is zero these sensors out from the very beginning, and I didn't do that. And so one more time, I'm going to zero these sensors out. Both of them, 0. And then 0. And one more time, I'm going to do what I just did, except I'm going to put them on the track so I can sort of hold on to it a little better. And I'm going to let this run one more time, and we're going to see what we get when we do it that way. So I'm going to hit collect, and I'm going to take these, and I'm just going to push them, push, 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 push. And notice here, once again, we see this nice symmetry. Now, the last thing I want to show you, because I think it's pretty cool, this program is nice because like if I asked you, oh cool guys, find the area under the curve for that graph, that's a bit of a pain because it's not a regular shape. Like you could say, yeah, we almost have a triangle from there, and then like we could do a little rectangle there, and then like a smaller rectangle, but it would be a nightmare. But on this program, if you select a certain space, then you can use the tools on this program to, as it says here, view the integral. And as you'll learn eventually, the integral in calculus is basically just the calculus version of finding the area under the curve. And when I hit view integral here, notice it says my positive area is almost the same as my negative area within a few tenths. And so the basic idea here is that since the forces are always equal and opposite, the areas under the curve here are basically always canceling each other out. And that's how you can tell that Newton's third law works. All of the stuff that we have been talking about, what I think is pretty cool about it is that back in Newton's day, Newton essentially just reasoned all of these things out, that these forces should be equal and opposite, and the areas should cancel each other out. And now that we have this fancy high-tech equipment, like these carts and these sensors, we can confirm that that's true. Pretty cool. Physics. See you guys.